Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and material subject. So in this subject already we have seen different types of beams and then different types of loads and how to draw the shear force diagram and bending moment diagram for different beams we have seen in the previous sessions. Today I want to discuss about some more beams, shear force diagrams and bending moment diagrams, how to draw and how to calculate shear force forces and then bending moments and then how to draw the shear force diagrams we will see in this session. So first of all, you will see the course outcome. So the course outcomes are many outcomes are there, total 6 outcomes. But regarding this shear force and bending moment diagram, the outcome is illustrate the shear force and bending moment diagram distribution in beams. So after completion of this course module, students are able to illustrate the shear force and bending moment distribution and also analyzing the structural behavior under various loads. So different types of loads under loads, different category loads, the student can able to analyze. So after completion of this module, they will learn. They will able to answer this type of for this shear force and bending moment distribution questions, and also they are able to illustrate the different diagrams for different beams. So first of all, for every beam, every shear force and bending moment diagram, any type of beam, the important points for drawing shear force and bending moment diagrams. So the following points are very important for drawing shear force and bending moment. One is consider the left or the right portion of the section. First, you have to divide the beam into two portions and then consider the left side or right side of the section. So, add the forces including reaction force normal to the beam on one of the portion. If right portion of the section is chosen, a force on the right portion acting downwards is positive, while a force acting upwards is negative. So one is, suppose your right portion of the section is chosen, force on the right portion acting downwards is positive, while a force acting upwards is negative. If the left portion of the section is chosen, a force on the left portion acting upwards is positive, and while the force downwards is negative. So the positive values of shear force and bending moments are plotted above the baseline. For every diagram, start with the baseline. The positive values of shear force and bending moments are plotted above the baseline. Suppose this is baseline, and below the baseline, you have to draw the negative values. So the shear force diagram will increase or decrease suddenly, that is by a vertical straight line at a section where there is a vertical point. So the shear force between any two vertical loads will be constant, and hence the shear force diagram between two vertical loads will be horizontal. The shear force between any two vertical loads will be constant. Hence the shear force diagram between two vertical loads will be horizontal. The bending moment at the two supports of the simply supported beam and at the free end of the cantilever will be 0. So the bending moment at the two supports of a simply supported beam at the free end of the cantilever will be 0. Simply supported and then cantilever beam. So here, see, uh, suppose in case of cantilever beam, is free end, fixed end, fixed end, free. So at this free end, the bending moment will be 0. Similarly, in case of simply supported beam, fixed end, so reaction forces RA and RB. So at the supports, the bending moment will be 0. These are the important points for every shear force diagram and bending moment diagram. So next now we will discuss about shear force and bending moment diagrams for a simply supported beam carrying a uniformly distributed load. In previous sessions already we have seen uniform simply shear force and bending moment diagrams for a simply supported beam carrying a point load. But in this session, so I want to discuss about uniformly distributed load. So here, take a simply supported beam. So the beam is like this, A and B with UDL load. So this is W for unit length. Okay. The length of the beam is L. So at this, the given take at their midpoint C. So the given load is UDL. Two supports are there, A and B. So that here, let assume RA and RB are the support reactions forces. Support reactions. So RA and RB. So here, clear. So RA and RB are the support reactions. Now, what is the force acting on this beam is equal to RA plus RB is equal to W into L. So total load UDL, that is W for unit length. So here the W is the UDL unit length. So this UDL is converted into point load, that is W into L. So here RA plus RB is equal to WL. First of all, calculate RA and RB. So RA is equal to WL by 2 and RB is equal to WL. Clear? So imagine here, assume the load is the UDL is acting per unit length, that is converted into WL. So RA plus RB is equal to W into L. So calculate reaction forces RA and RB, taking moments of forces at about A or about B you can take. So that is, after calculation, calculate RA and RB, will get WL by 2 into W. So WL by 2 RA and RB is equal to W. So now take section at take section, that is X from its left side, from its left side support, that is RA, with the distance X. So take section. So here you can take section XX with the distance X. Clear? So here need to calculate shear force at this section, and also calculate bending moment at this section. Must you calculate shear force and bending moment. So here, what is the shear force at section XX? The shear force the shear force at section X, that is Fx. So what are the forces acting at this section left side? So that is vertical, that is supported force, that is RA. So RA, what are the forces acting? RA minus at this section W is acting, so that is W into X. RA minus W into X. Shear force acting at this section is RA minus WX with X distance. So now calculate shear forces at different points. So at shear force at point A. At point A. So the point A means that is X is equal to 0. So now calculate the shear force at point A, RA minus W to 0. So that is RA. So what is RA? WL by 2. Similarly, shear force at B. at B. At B is, here RB, what is the shear force at B point? So RA minus W into what is the B? The X distance is L. So that is WL by 2 minus WL. So minus WL by 2. So negative value at B, the shear force. Similarly, shear force at C point. Shear force at C. FC. So X is equal to, what is the X value at C? L by 2. So here, therefore, RA minus W into L by 2. So WL by 2. So substitute here. Shear force at B is equal to minus WL by 2 and A is equal to WL by 2. At C, the shear force acting is, so take above the distance L by 2, W into L. So that is already written here, RA minus W into X. The X value is here, the distance is from its left side L by 2. So that the shear force is at this section C, RB minus W into L by 2. So WL by 2 minus WL by 2 equal to 0. So now according to the calculated values, draw the shear force diagram. So it means it follows, the diagram is straight line law, so that, so the diagram, see here, WL by 2, the RA positive and negative is equal to minus L. It changes its sign. So here, let's see, there is no shear force here 0, that is positive Fx2 minus this Lb2 and Lb2 baseline. So these negative values below the baseline and positive values above the baseline. This is regarding the shear force diagram. Now similarly, find out the bending moments at various points, and then bending moment diagram. See, bending moment at section X, that is Mx, So here the bending moment is the RA into X minus RA into X minus W into X into X by 2. So this is the equation for bending moment. Now calculate BM bending moment values at different points. Different points. So first at A, that is x is equal to 0. The bending moment is WL by 2 and 0. So multiply with 0, 0. So entirely the bending moment at A is equal to 0. Why? Because at their supports there is no bending moment. Similarly, at B, at B, at point B, the bending moment is, so at point B, that is, sorry, at point B, x is equal to L. So here substitute the bending moment at B, RA WL by 2 multiply with L minus W into L into L by 2. Here WL square by 2 minus WL square by 2. So we'll get 0. So at their section, sorry, at their supports, there is no bending moment. Now calculate bending moment at C point. So at a bending moment at C point, MC, that is x is equal to L by 2. Now substitute RA into x minus W into x by 2. So RA WL by 2 into L by 2 minus W into L into L by 2. So here, so WL square by 4 minus WL square by 2. So we will get after simplification WL square by 8. So this is a positive value. So here the BM bending moment increases according to the parabolic law. 0 at A to WL square by 8. The middle point of the beam. And from this value, the bending moment decreases to 0 at B according to the parabolic law. So at their A point, 0, and then increases and again 0. So it means, so this is maximum bending moment. This one also 0, B and A. So it means it follows parabolic law. So according to calculated values, now draw bending moment diagram. So here bending moment at C point calculated, and A and B, A at 0 and B 0, and then now draw the bending moment diagram. So as shown in figure, the bending moment. Shear force is already over. So below the shear force, draw the bending moment diagram. So A and B supported reactions, and then W square by 8 is the maximum bending moment occurs at middle C point. So this is positive bending moment, the baseline, and then positive bending. See here for a shear portion bending moment diagram shown for a simply supported beam carrying uniformly distributed load. So in next type is you'll see here the shear portion bending moment diagrams for a simply supported beam with an eccentric point load. The previous case in the first session have seen at its center point load, but here load is not acting at its center. UDL already we have discussed, and the point loads also earlier sessions we have discussed. But in this problem, in this case, the shear force bending diagram for a simply supported beam with an eccentric point load. So eccentric point load they're not at its center. The load is acting from its support to with a distance A, and remaining from its B support B. The total length of the beam is L. The section taken in between A and C is X. So how do you calculate? First of all, calculate the uh, reaction forces RA and RB. So here RA plus RB is equal to W. So what are the forces acting here? Is equal to upward forces are equal to downward forces. So RA plus RB is equal to W. So RB or RA. So first this equation now written like this as 1. Right? This equation. And then for remaining force calculation, taking moments of forces about its A or about its B. So remaining forces RB into L is equal to W. So taking moments here, taking moments of forces, taking moments of forces about A or B. So taking about A, RB into L is equal to W. W into, so here W into the up to C point is the distance is A. So W into A. So now RB you can calculate W into A by L. So now substitute this value RB in this RA plus RB. We will get RA value. How do you calculate? So RA plus RB is equal to W. So RB already have calculated by taking moments forces about A, WA by L. So RA plus WA by L is equal to W. So RA is equal to W minus WA by L. So take common W outside. Here 1 minus A by L. Clear? So now you can write this equation W into L minus A by L. So what is this W into L minus A by L? So W into L minus A. So what is this L minus A? As per a diagram, L, the total length, and the A distance from its one support, left side support to load. That is A, L minus A. So L minus A is equal to B. Okay. So B by L. So now the RA is equal to W by L. RB is equal to W by L. Okay. So your reaction forces are calculated. Now calculate shear force. So shear force at what is the shear force at section X? So take section A between A and C. What is the shear force at section X? RA. The shear force is at A and RA minus what is the force acting here up to X. So here W RA is equal to W into B by 2. So here if you calculated the RA W by L already you know, and the RB W by L. So the RB is equal to the shear force changes its sign from positive to negative. So it means here at C the value will be negative. Clear? So here W by L RA and RB at RB is equal to W by L already you calculate at C. So how do you calculate shear force at C? At section set C at a point C, the shear force that is Fx, Fc. What is the distance here up to C? Distance dA. So now substitute the x value, that is x is equal to A. So now calculate the shear force RA minus W. into A. So W into X actually. That is substitute after substitution W by A. Now the RA is calculated in the previous year. The RA is W by 2. So W by 2, sorry, WB by 2 minus W by A. So take common here, W will be by 2 minus A. Now after simplification this one, you will get at C shear force. Clear? So and then draw the shear force diagram. Similarly, calculate bending moment. So the bending moment so the bending moment equation bending moment at section X, that is MX, RA into X, RA into X. Now calculate bending moment at different points. So here shown in diagram, at the supports already you know the bending moment is 0. So now need to calculate bending moment at C. Suppose you calculate at A point, that is X is equal to 0. So your bending moment RA is equal to WB by L multiply with 0. So 0. At B point, that is X is equal to L. X is equal to L. Now calculate bending moment at B. RA W A by L multiply with L. At C point, that is the X is equal to A. So RA W by L to X is equal to A. So WAB by L. So B by L into A. So WAB by L. MC. Clear? So now draw the bending moment diagram. WAB by L at its point C shown in this diagram, and then shear force. So like this, you have to calculate the shear forces and bending moment diagrams for a given beam. Suppose the type of beam is given UDL, need to apply the UDL conditions. Suppose point load application, point load the apply load is point load. So the point load rules you need to apply. So here, in this case, this is not a point load and not a UDN. If the load is acting, the point load is acting with an eccentric with some distance, not exactly its center. So that's why this type of load is called as eccentric point load. So need to calculate all forces at this point. So take section X and then calculate the forces and then shear forces and the bending moments. So according to this, you need to draw the diagrams. So in this, for this preparation of PPT, I have taken references as Ramamrutam. The title of the book is Strength of Materials, and then R.K. Hasbut, Strength of Materials, and then publications, and R.K. Bansal, the textbook of Strength of Material, and R.S. Kurmi and Gupta. These are the references I have taken. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.